A directed energy weapon emits highly focused energy, transferring that energy to a target to damage it. Potential applications of this technology include anti-personnel weapon systems, potential missile defense system, and the disabling of lightly armored vehicles such as cars, drones, jet skis, and electronic devices such as mobile phones. The energy can come in various forms. Electromagnetic radiation, including radio frequency, microwave, lasers and masers. Particles with mass, in particle beam weapons. Sound, in sonic weapons. Operational advantages. Laser weapons could have several main advantages over conventional weaponry. Dews can be used discreetly as radiation above and below the visible spectrum is invisible. Laser beams travel at the speed of light, so evading an accurately aimed laser after it has been fired is impossible. Consequently, there is no need to compensate for target movement. Light is only very slightly affected by gravity, so that long-range projection requires virtually no compensation. Other aspects such as wind speed can be neglected at most times, unless shooting through an absorptive matter. Lasers can change focusing configuration to provide an active area that can be much smaller or larger than projectile weaponry and fire at multiple targets simultaneously. Given a sufficient power source, laser weapons could essentially have limitless ammunition. Because light has a practically zero ratio of momentum to energy, lasers produce negligible recoil. Lasers and particle beams can be fired off-axis without physically moving the beam emitter. Laser beams do not generate sound, so the weapon would not betray its user's position when fired. Lasers and particle beams cannot be deflected or intercepted with point defense hard-kill countermeasures. Types. Microwave weapons. Although some devices are labeled as microwave weapons, the microwave range is commonly defined as being between 300 MHz and 300 GHz, which is within the RF range. Some examples of weapons which have been publicized by the military are as follows. Active denial system is a millimeter wave source that heats the water in the target's skin and thus causes incapacitating pain. It is being used by the U.S. Air Force Research Laboratory and Raytheon for riot control duty, though intended to cause severe pain while leaving no lasting damage. Some concern has been voiced as to whether the system could cause irreversible damage to the eyes. There has yet to be testing for long-term side effects of exposure to the microwave beam. It can also destroy unshielded electronics. See Tempest. The device comes in various sizes including attached to a Humvee. Vigilant Eagle is an airport defense system that directs high-frequency microwaves towards any projectile that is fired at an aircraft. The system consists of a missile detecting and tracking subsystem, a command and control system, and a scanning array. The MDT is a fixed grid of passive infrared cameras. The command and control system determines the missile launch point. The scanning array projects microwaves that disrupt the surface-to-air missile's guidance system, deflecting it from the aircraft. Bofors HPM Blackout is a high-powered microwave weapon system which is stated to be able to destroy at distance a wide variety of commercial, off-the-shelf electronic equipment. It is stated to be not lethal to humans. The effective radiated power of the LM-2080 Green Pine radar makes it a possible candidate for conversion into a directed energy weapon. By focusing pulses of radar energy on target missiles, the energy spikes are tailored to enter missiles through antennas or sensor apertures where they can fool guidance systems, scramble computer memories or even burn out sensitive electronic components. AESA radars mounted on fighter aircraft have been slated as directed energy weapons against missiles. However, a senior U.S. Air Force officer was quoted noting, They aren't particularly suited to create weapons effects on missiles, because of limited antenna size, power and field of view. Potentially lethal effects are produced only inside 100 meters range, and disruptive effects at distances on the order of 1 kilometer. Moreover, cheap countermeasures can be applied to existing missiles. General information on lasers. Lasers are often used for sighting, ranging and targeting for guns. In these cases, the laser beam is not the source of the weapon's firepower. Laser weapons usually generate brief high-energy pulses. A 1 megajoule laser pulse delivers roughly the same energy as 200 grams of high explosive, and has the same basic effect on a target. Most existing weaponized lasers are gas dynamic lasers. Fuel, or a powerful turbine, pushes the lasing media through a circuit or series of orifices. The high pressures and heating cause the medium to form a plasma and laze. A major difficulty with these systems is preserving the high-precision mirrors and windows of the laser resonating cavity. Most systems use a low-powered oscillator laser to generate a coherent wave, and then amplify it. Some experimental laser amplifiers do not use windows or mirrors, but have open orifices, which cannot be destroyed by high energies. Some lasers are used as non-lethal weapons, such as dazzlers, which are designed to temporarily blind or distract people or senses. Electrolaser. An electrolaser lets ionization occur, and then sends a powerful electric current down the conducting ionized track of plasma so formed. Somewhat like lightning, it functions as a giant high-energy long-distance version of the taser or stun gun. Pulsed energy projectile. Pulsed energy projectile or PEP systems emit an infrared laser pulse which creates rapidly expanding plasma at the target. The resulting sound, shock and electromagnetic waves stun the target and cause pain and temporary paralysis. The weapon is under development and is intended as a non-lethal weapon in crowd control. Examples: in 1984, the Soviet Strategic Missile Troops Military Academy developed the first handheld laser weapon, intended for use by cosmonauts in outer space. In 1987, a Soviet laser-armed orbital weapon system, the 17F-19DM Polyush Skiff-DM, failed during deployment. In 1991, scientists at the U.S. Army Missile Command developed and field-tested a ruggedized tunable laser emitting an yellow-orange-red part of the spectrum, made by Northrop Grumman. On March 18, 2009, Northrop Grumman announced that its engineers in Redondo Beach had successfully built and tested an electric laser capable of producing a 100-kilowatt ray of light, powerful enough to destroy cruise missiles, artillery, rockets and mortar rounds. An electric laser is theoretically capable, according to Brian Strickland, manager for the United States Army's Joint High-Power Solid-State Laser Program, of being mounted in an aircraft, ship, or vehicle because it requires much less space for its supporting equipment than a chemical laser. On April 6, 2011, the U.S. Navy successfully tested a laser gun, manufactured by Northrop Grumman, that was mounted on the former Paul Foster, which is currently used as the Navy's test ship. When engaged during the test that occurred off the coast of Central California in the Pacific Ocean Test Range, the laser gun was documented as having a destructive effect on a high-speed cruising target, said Chief of Naval Research Admiral Nevin Carr. While classified, the proposed range of the laser gun is measured in miles, not yards. Northrop Grumman has announced the availability of a high-energy solid-state laser weapon system that they call FIRESTRIKE, introduced on 13 November 2008. The system is modular, using 15 kilowatts modules that can be combined to provide various levels of power. On 19 July 2010, an anti-aircraft laser described as the Laser Close-In Weapon System was unveiled at the Farnborough Air Show. The Zeus HLONS is the first laser and the first energy weapon of any type to be used on a battlefield. It is used for neutralizing mines and unexploded ordnance. Laser Area Defense System. The mid-infrared advanced chemical laser is an experimental U.S. Navy deuterium fluoride laser and was tested against an Air Force satellite in 1997. In 2011, the U.S. Navy began to test the Maritime Laser Demonstrator, a laser for use aboard its warships. In 2013, the U.S. began field testing a directed energy weapon it calls the Laser Weapon System. Personnel Halting and Stimulation Response, or PHASR, is a non-lethal handheld weapon developed by the United States Air Force. Its purpose is to dazzle or stun a target. It was developed by Air Force's Directed Energy Directorate. Tactical high-energy laser is a weaponized deuterium fluoride laser developed in a joint research project by Israel and the U.S. It is designed to shoot down aircraft and missiles. See also National Missile Defense. Soviet-Russian Beriev A-60, a CO2 gas laser mounted on an Ilyushin Il-76MD transport. The U.S. Air Force's Airborne Laser, or Advanced Tactical Laser, was a plan to mount a CO2 gas laser or coil chemical laser on a modified Boeing 747 to shoot down missiles. High-energy laser mobile demonstrator is a Boeing-designed laser system mounted on a heavy expanded mobility tactical truck. Its current power level is 10 kilowatts, which will be boosted to 50 kilowatts, and expected to eventually be upgraded to 100 kilowatts. Targets that can be engaged are mortar rounds, artillery shells and rockets, unmanned aerial vehicles, and cruise missiles. Lockheed Martin is developing a 60 kilowatts fiber laser to mount on the HELMD that maintains beam quality at high power outputs while using less electricity than solid-state lasers. Portable efficient laser testbed. Laser aircraft countermeasures. See also electrolaser # examples of electrolasers. Problems. Existing methods of storing, conducting, transforming, and directing energy are inadequate to produce a convenient handheld weapon. Existing lasers waste much energy as heat, requiring still bulky cooling equipment to avoid overheating damage. Air cooling can yield an unacceptable delay between shots. These problems, which severely limit laser weapon practicality at present, might be offset by cheap, high-temperature superconductors to make the weapon more efficient. More convenient high-volume electricity storage generation. Part of the energy could be used to cool the device. Chemical lasers use energy from a suitable chemical reaction instead of electricity. Chemical oxygen iodine laser and deuterium fluoride laser are two laser types capable of megawatt range continuous beam output. Managing chemical fuel presents its own problems, and issues with cooling and overall inefficiency remain. These problems could be lessened if the weapon were mounted either at a defensive position near a power plant, or on board a large, possibly nuclear-powered, water-going ship, as it would have the advantage of plentiful water for cooling. Blooming laser beams begin to cause plasma breakdown in the atmosphere at energy densities of around 1 megajoule per cubic centimeter. This effect, called blooming, causes the laser to defocus and disperse energy into the surrounding air. Blooming can be more severe if there is fog, smoke, or dust in the air. Techniques that may reduce these effects include spreading the beam across a large, curved mirror that focuses the power on the target. To keep energy density en route too low for blooming to happen, this requires a large, very precise, fragile mirror, mounted somewhat like a searchlight, requiring bulky machinery to slew the mirror to aim the laser, using a phased array. For typical laser wavelengths, this method would require billions of micrometer-size antennae. There is currently no known way to implement these, though carbon nanotubes have been proposed. Phased arrays could theoretically also perform phase conjugate amplification. Phased arrays do not require mirrors or lenses, and can be made flat and thus do not require a turret-like system to be aimed. though range will suffer if the target is at extreme angles to the surface of the phased array. Using a phase conjugate laser system, this method employs a finder, or guide, laser illuminating the target. Any mirror-like points on the target reflect light that is sensed by the weapon's primary amplifier. The weapon then amplifies inverted waves in a positive feedback loop, destroying the target with shock waves as the specular regions evaporate. This avoids blooming because the waves from the target pass through the blooming, and therefore show the most conductive optical path. This automatically corrects for the distortions caused by blooming. Experimental systems using this method usually use special chemicals to form a phase conjugate mirror. In most systems, the mirror overheats dramatically at weapon useful power levels. Using a very short pulse that finishes before blooming interferes, focusing multiple lasers of relatively low power on a single target. There are several approaches to this problem. Inducing a standing shockwave in the ablation cloud. The shockwave then continues to inflict damage, scanning the target faster than the shockwave propagates. Inducing plasmic optical mixing at the target by modulating the transparency of the target's ablation cloud to one laser by another laser, perhaps by tuning the laser to the absorption spectra of the ablation cloud, and inducing population inversion in the cloud. The other laser then induces local lasing in the ablation cloud. The beat frequency that results can induce frequencies that penetrate the ablation cloud. Beam absorption. A laser beam or particle beam passing through air can be absorbed or scattered by rain, snow, dust, fog, smoke, or similar visual obstructions that a bullet would easily penetrate. This effect adds to blooming problems and makes the dissipation of energy into the atmosphere worse. The wasted energy can disrupt cloud development since the impact wave creates a tunneling effect. Engineers from MIT and the U.S. Army are looking into using this effect for precipitation management. Lack of indirect fire capabilities. Indirect fire, as used in artillery warfare, can reach a target behind a hill, but is not feasible with line-of-sight use. Possible alternatives are to mount the lasers on airborne or space-based platforms. Countermeasures. The Chinese People's Liberation Army has invested in the development of coatings that can deflect beams fired by U.S. military lasers. Lasers are composed of light that can be deflected, reflected, or absorbed by manipulating physical and chemical properties of materials. Artificial coatings can counter certain specific types of lasers. But if a different type was used than the coating was designed to handle, it would be able to burn through it. Available information on a system's size, power consumption, major components, and laser generation methods can determine the type of laser beam and which type of coating. The coatings are made of several different substances including low-cost metals, rare earths, carbon fiber, silver, and diamonds that have been processed to fine sheens and tailored against specific laser weapon systems. China is developing anti-laser defenses because protection against them is considered far cheaper than creating competing laser weapons themselves. China is some 10 to 20 years behind the United States in development of laser weapons due to energy generation and storage problems. Particle beam weapons. Particle beam weapons can use charged or neutral particles, and can be either endoatmospheric or exoatmospheric. Particle beams as beam weapons are theoretically possible, but practical weapons have not been demonstrated. Certain types of particle beams have the advantage of being self-focusing in the atmosphere. Blooming is also a problem in particle beam weapons. Energy that would otherwise be focused on the target spreads out, the beam becomes less effective. Thermal blooming occurs in both charged and neutral particle beams. and occurs when particles bump into one another under the effects of thermal vibration, or bump into air molecules. Electrical blooming occurs only in charged particle beams, as ions of like charge repel one another. Plasma weapons fire a beam, bolt, or stream of plasma, which is an excited state of matter consisting of atomic electrons and nuclei, and free electrons if ionized, or other particles if pinched. The Marauder used the Shiva Star project to accelerate a toroid of plasma at a significant percentage of the speed of light. Electric beam in a vacuum. An electric discharge can travel at potentially unlimited distance at a velocity slightly slower than the speed of light. This is because there is no significant electric resistance to the flow of electric current in a vacuum. This would make such devices useful to destroy the electrical and electronic parts of satellites and spacecraft. However, in a vacuum the electric current cannot ride a laser beam, and some other means must be used to keep the electron beam on track and to prevent it from dispersing. See particle beam. Speed of the weapon. The speed of the energy weapon is determined by the density of the beam. If it is very dense, then it is very powerful, but a particle beam moves much slower than the speed of light. Its speed is determined by mass, power, density, or particle energy density.